Welcome back. Last week we put together our dual engine control lever IP68 thingy here, and it works quite fine. Card here, link in the description. But I noticed, well, I was aware of it quite some time, but then I really realized that our A1335 Allegro precision Hall effects angle sensors inside here are not really sensing a continuous 360-degree angle, but only something like plus minus 60 degrees. And that's called a short stroke application, when you not go most of the whole circle, but only, a part of the circle. And in this case, we're doing about a third of the circle. It's been a while. I think it was August last year when we did the last bit of Arduino software here for our A1335 Hall effect angle sensor. Card here, link in the description. And I think in the intro to those videos I mentioned that I won't touch the short stroke stuff. That is actually supported, not by the Arduino, but by the A1335s inside here. So we will, in this 9th video about the details of the A1335, revisit all that short stroke stuff. Enjoy! Now, before we dive into things, if I remember right, in the last video, left and right were swapped. And yeah, I'm changing here the right lever, or the port engine lever, hint, hint. And we are actually changing here the right column, and if I do the right lever, we are changing the left column. Okay, just a sec. If you don't remember the code anymore, don't worry. I don't remember it either, but it's all done with constants here, and we just have to exchange the I2C addresses of our chips, and then everything should be working fine, hopefully. And indeed, left is left again and right is right. So that's nice. Next problem was the orientation. So what's a decreasing angle and what's an increasing angle? And I want the angles to increase if I go, forward here. And currently that's not the case for the left side. Obviously the angle is decreasing if I rotate here. And for the right side, the angle is indeed increasing. So that's perfect. But we have to change that on the left side. And if you remember that big picture with all the functionality of the A1335, that was this little option here. The prelinearization rotation, P2A, which we fortunately already implemented in one of the previous videos. So further down, beside the left and right I2C address, we should have, or I already added it, the constants for the A1335 left prelinearization rotation clockwise flag and right prelinearization clockwise flag. Right was okay, so we leave that. And I set the option for the left one to actually prelinearization rotation clockwise. And then there I changed a little bit around the code here. I think we have the general bit mask for the flags we want to set for the algorithm. And here the only bit we really want to set currently is the algorithm prelin rotation clockwise. And then I have here two more constant expressions for the left algorithm bits and the right algorithm bits. And here we use, of course, the two constants we defined already up here. And within our setup, we of course set these algorithm bits for our left and our right chip here, object, A1335 object that is, with the left algorithm bits and the right algorithm bits, and yeah, the appropriate bit masks, which contains only that one bit now for, yeah, clockwise, counterclockwise. And if we have a look again at the serial monitor and we push now our power lever here on the left forward, we see the angle is increasing. Perfect. And yeah, for the right one, that was correct in the first place. Okay, I think now we get into some actually new territory. What I want to achieve now is that this position here on both sides reads as 0. And later on, yeah, that's in the following steps, that position here will read at 360 degrees. You might ask, why not set, yeah, the neutral position at 0? But this will, as you will see later on, interfere with our linearization stuff. So for the linearization to really work, we need a continuous 0 to maximum sweep here. So let's start by setting that here to 0. Again, we are in our function overview. We already did that optional prelinearization rotation stuff here, and now we're going here to the optional gain offset. A little further down in the datasheet, it simply states, yeah, gain offset allows zeroing out of the angle prior to applying gain, which we will do next. And angle is equal to angle minus that gain offset. And within the programming manual, we are told that is at the SRAM address 0x03, the gain offset. Just the two most significant bytes of the whole 32-bit word. And further down, we get some more information about that register. Nothing too much though, a lot of text here about how that field is initialized from the EEPROM. We're not really interested in that, and that the gain offset is subtracted from the angle that we are actually measuring. And this operation is performed whether the flag SS, so short stroke application, is set or not. So we don't need for now to set that flag SS. And most important here, it's a 16-bit value, 2 bytes, and a little cryptic offset value in angle resolution units. My best guess, that means that the value 0x10000, so one more than 0xFFFF, is 360 degrees. And 0 is 0 degrees, of course. The implementation is trivial because of all the work we've already done. So we have here for all the SRAM registers already created some constants. Here is our extended RAM gain offset gain address register address hexadecimal 3. And if you remember the segmented linearization offset methods here we've implemented in the 6th installment about the details of the A1335 card here, link in the description. They are very similar to our now to be implemented gain offset methods. So nothing new there. And indeed, if you have beforehand a look at these segmented linearization offset methods here, I really just copy and pasted them into two new methods for our gain offset. The code is the same, just the name of the parameter is changed here, and of course the register address we are writing to. And yeah, same is true for the gain offset. So have a look again at that sixth installment where I go over these functions in detail. Now, if we take some measurements of our angle readings in our fully backward position, then that's for the left handle here, 331 degrees. But we know we have some crosstalk, so that might go down to 330 point something. And for the right side, we're at 290 something, and we have negligible crosstalk there. So some crosstalk, but yeah, it's just unidirectional. Interesting. So we introduce in our code some new constants here, or constant expressions. For the left gain offset 330, that should get us almost to 0 on the left side. And for our right sensor 290. Remember, these are subtracted from the actual readings. That should also get us close to 0. And further down at the very end of the setup, we are calling our new methods. Where are they? Here. So set the gain left gain offset and the right gain offset with the correct constants, of course. And if anything should go wrong, we print the error and we say not working. And indeed, if we have a look now at our serial monitor, we are here in the back position and we're near 0 for both. Yeah, you could fine tune that. And yeah, we go up to about-ish, let me see, almost 120 degrees. So yeah, it's plus minus 60 degrees here. Wonderful. So we successfully set our gain offset here, and the next step in the processing would be a check of the minimum maximum angle. But we skip that for now. That function would allow us to throw an error as soon as the angle readings get out of a certain range. For example, a bolt is going out here or brakes, and then we would read some engine commands which don't really make sense. So it's an important function, but we will do this at the end. Instead, we shall continue with a gain adjust, which will allow us to spread our 0 to 120 degree readings to a full 0 to 360 degree scale. The information about that function in the datasheet is a little bit meager. It's just important for us to note that this feature is only active if short stroke bit has been set. So we need to do that too. The gain can be found at the same hexadecimal 3 SRAM register address as the gain offset, but it occupies the 2 least significant bytes. The detailed information about these 2 gain bytes in the programming documentation is a little bit anyway. We need to set the SS flag in our algorithm register, otherwise that function won't work. We shouldn't use a gain greater than 16, that has to be entered as 15.00, meaning that the most significant 4 bits are always 0 or should always be 0. Yeah, the 16 and 15 is based in the fact that the gain scale factor we are writing here is -1. So if we write 0 to our register, that is a gain of 1. So you cannot create any gains smaller than 0. Wouldn't make any sense. Anyway, from the rest here, it's nowhere explicitly stated. You can derive that your decimal value here is the binary value divided by hexadecimal 1 and then 8 zeros. So we basically have here a floating point number. Not a floating point, a fixed point number, where the last byte here represents the decimals. The other way around, if we want to calculate the binary value here, we have to take the decimal value of our gain and multiply it by hexadecimal 100000000. We've already implemented all the algorithm enable flags here, so also the algorithm short stroke mode SS flag. So all we need is a new function gain here in 2 different versions. As always, the raw binary value and then our convenient function with a float, quite analog to the gain offset we've already implemented. The scaling here is a little bit more tricky. I mentioned that when we looked at the data sheet. So the binary version gets a gain raw, and the gain is actually the gain raw divided by hexadecimal 0100 plus 1. So the range of the gain raw value we can pass here is between 0 and 0F00 hexadecimal. When I talked about that in the datasheet, I mixed up binary. I gave you the binary values here and not there and not the hexadecimal values. Anyway, then our convenience function gain factor, that's directly the gain, and the value range is between 1 and 16. The implementation is of course also analog. We check if here for our integer version, unsigned integer version, the value is within the range. Otherwise we throw in a library error, and then we write the whole thing to the extended RAM gain offset gain address. But this time we write it to the lower 2 bytes. Our convenience method here with a float argument works exactly the same. We check here the range of our parameter and throw a library error if we are out of range. And then we scale the whole thing here to the binary value range. And yeah, that's also something we saw before. Just making sure here we don't have any float error that gets us, be above the 16 here. And then we round that here to an unsigned int and call our raw gain setting function. In the sketch itself, we define 2 new constants here for the left and the right gain. We saw when we went to the full throttle position, full ahead throttle position, we were just shy of 118 degrees. So the gain we desire to get a full 360 at full throttle is 360 divided by the 118 we saw. And then in our setup, right after we set the gain offset, we set the gain for the left and the right sensor. And of course, throw an error if something goes wrong. And that's how the whole thing looks on the serial monitor. So we are here at our 0 positions here, so that would be full astern, and our 0 position is now aboutish 180 degrees. Yeah, some non-linearity there, but that's okay. And if we go full ahead, we're close to 360 degrees. So we have achieved full scale now for our full 360 degree scale. Now for our little less than 120 degree movement. Great. So we did our angle gain offset and our gain adjust here. We still skipping that minimum maximum angle check, and the next option we have here is the angle clamping. The angle clamping stuff sits at the SRAM register 02. And 2 bytes, most significant bytes for a high clamp value, and 2 least significant bytes for the low clamp value. The datasheet gives us a clear description of that P6 function, angle clamping. If the output signal exceeds the other clamp, the output will stay at the clamp value. If the output is lower than the lower clamp, the output will stay at the low clamp value. And of course, this feature is only active if the short stroke bit has been set. The programming manual dedicates a whole page to that stuff, but doesn't add much new. The important informations here are that, the scale is 360 degrees divided by 65,536, so 2 to the power of 16. And that's it. To disable the function, the high clamp, set it to the maximum value, and to disable the low clamp function, set it to 0. The implementation varies a little bit to what we've done before. First, please note I started changing the headings here to actually reference the datasheet. It doesn't make any sense to repeat here in the heading what's coming down below anyway. Let's continue. This time we're writing two 16-bit words to the same 32-bit register, and it doesn't make any sense to write the low and the high clamp angles in different calls. You will always write them in one call. So our binary version here with the unsigned integers as argument, nothing special here. So our low angle is low divided by the 2 to the power of 16 times 360 degrees. And then we have our convenience function here with the float arguments directly in degrees, and here the value range is between 0 and just below 360. The implementation for clamp angles for the integers is trivial. We just shift the two integers into a 32-bit word, and we write that to our extended address, extended RAM clamp high low address. The float version is a little bit more complicated and bloated, but that's also because I have some code duplication here, but I didn't bother with that, at least not at this point. So first we check our value ranges and throw, as usual, a library error if something is out of the order. And then we scale both values here to 360 degrees is full scale 2 to the power of 16. We take care of any rounding errors that would get us in the integer value below 65535. And then we call our binary version with the scaled to integer arguments. In our sketch, we have 4 new constants for the left and the right sensor, the clamp angle low and the clamp angle high, and I choose here just for the low angles 5 degrees and for the high angles 350 feet, 55 degrees. And of course, we call our new method clamp angles here 2 times and yeah, if necessary, throwing an error in our setup. Anyway, here's our output on the serial monitor, and if I go to our lowest position, we get out 4.92 degrees. Now clamped, so it doesn't go lower than that. And this is actually a rounding error. Yeah, we get not exactly 5 degrees in binary anyway. It's 4.9 something. And then the output angles from the A.335 are rounded again to 12 bits, not the full 16 bits, which we use internally for our calculations. Anyway, maximum position, yeah, we're almost spot on. Just a little rounding error here. But this is now very nice in an application where you really need a fixed minimum and maximum value. Because there you see our min and max values for both channels are now exactly the same. So this looks actually quite usable, and yeah, here in the middle a little wiggle now because of the scaling, a little bit amplified. We have to take care of that, but that's not the job of the A1335. But otherwise, it works quite well. Before we implement the last more complex function, the minimum and maximum angle check, which will be trivial now, honorable mention of the optional angle inversion flag here. So this happens after the already mentioned rounding to 12-bit values for the angle, and it simply inverses things. So our low position would then be approximately 360 degrees and our high position would be 0 degrees approximately. Yeah, there's a formula for that, and of course this is only active if the short stroke bit has been set. And we find that as a simple flag within our algorithm enable register here in the SRAM. That's the IV, which is called simply invert angle. So 0, do nothing, and 1, invert the angle. And we already implemented that flag here in our algorithm enum. Where is it? Here, the algorithm short stroke invert, the IV flag. Onwards to the last functionality in conjunction with short stroke applications, and really the last function we will talk about today, and that's the minimum maximum angle check, which happens after we set the gain offset. That's what the datasheet is saying. P3 minimum maximum angle check short stroke applications only. That is, we need to set that short stroke bit, otherwise this function won't work. And we program it using 2 registers here, a min angle S and a max angle S. And if the angle, after we applied the gain offset here, is below the minimum or above the maximum, then one or the other error flag is set here, RAH, high boundary violation, or RAL, low boundary violation. And again, we have a whole page dedicated to that functionality in the programming manual. I won't even go into the details because that max angle and min angle, programming wise, they work exactly like our angle clamps. Yeah, max angle clamp and min angle, or high angle clamp and low angle clamp, exactly the same. Here are the prototypes for our P3 minimum maximum angle check, which are from the types and how you call them exactly the same like the angle clamp functions. So angle check with the integers, and inside the integer there is of course an angle encoded in 16 bits unsigned, and angle check with the floats, and inside there is well, the float is the angle, so range between 0 and smaller than 360. And again, I can't think of any situation where you just want to set one L value but not the other. So again, two arguments here. The implementation of both methods was a simple copy and paste of the clamp angles functions methods. So yeah, it's really exactly the same, just the name of the methods and the variables, they have changed. Otherwise, there is absolutely no difference. It's, yeah, copy and paste and then search and replace, as I said. In the sketch we have 4 more constants here which describe our range of motion. Yeah, just I estimated them. And somewhere in our setup we call the functions with these constants. Exactly the same way like we called the angle clamping stuff. And in normal operation nothing should happen. Yeah, it works like before, but if I lose a screw just for you, yeah, I have a screw loose, I know, the following should happen. We're going over our minimum and yeah, there it is. We are throwing an error for our left angle. That's it for today. We basically covered all of the short stroke functionality of our Allegro A1335 Precision Hall Effect Angle Sensor. I'm not quite sure what I will do next, but anyway, until next time, bye.